going to look at a special case for kinematics, one-dimensional motion, one-dimensional kinematics, where we're going to look at an object in free fall. And what we mean by free fall is not that it's falling, is that we have one force that's acting on it, and the only force that's acting on it is the gravitational force, the pull of the Earth down. And so in free fall, we say our acceleration is equal to a constant 9.8 meters per second squared in the j-hat direction, right? So that would be down in the y direction, or the downward y direction. And oftentimes you'll see this written as a is equal to minus g in the j-hat direction, where g in our convention is always positive. This is useful as you look at equations later on. This g is always positive, 9.8 meters per second squared, or 32 feet per second squared. And so the idea here is that even for an object that's going up and coming back down, the acceleration that it's experiencing is this acceleration due to gravity. So we're neglecting air resistance. We're saying after it leaves the hand, like this ball, after it leaves my hand and goes up and down, and we'll ignore air resistance. If that's the case, then what we're going to be doing is looking at our three equations for constant acceleration and modifying them slightly. So whereas we had x, we're going to actually write this as y is equal to y initial, the initial y naught, v0 t, where this is the initial velocity times time, and usually it's plus 1/2 at squared, or we can write this as 1/2 gt squared. Notice this is the same equation we had before. I've just plugged a g in place, where this g we know is 9.8. Similarly, we have v is equal to v0 minus g times t, or v squared is equal to v naught squared. This time, instead of a plus 2a, we're going to do a minus 2g y minus y naught. Okay, and so these are our equations of motion. If we graph them out, remember I said that graphing things is often a useful approach. If we take something like this golf ball that I throw up and then catch, then we can talk about the place where it leaves my hand as the initial y, call that y0. So I might set up my axis to look like this. So y versus t, I might start from 0. It would go up to its maximum height and then comes back down. And if you look at this equation, this is a second order equation. We go as t squared, so it's a parabola. It's supposed to be a symmetric parabola. I didn't draw it very well. But this is, it goes up and then comes back down. And then if we draw this velocity versus time, notice after it leaves my hand, that would be the v naught. So that's a positive slope, and that's really our biggest speed, right? Because our acceleration is down. This slope is 0, which means our v is 0 at the top. So it goes to the top and turns around. So this point, whatever time that is, that's halfway through its time, is where the velocity is equal to 0. So it starts positive, 0, and goes negative, and the slope here is constant, and it's equal to minus 9.8, right? That's the value of the slope in meters per second squared. And so if I let this golf ball go up and come back down and go past my hand, then of course this would go below 0, and this would keep going, and it would just keep getting faster and faster until it hit the floor. So that's how we set these up, and we can read the information. Some other information we can read here is, remember that the slope of the velocity versus time gives you the acceleration, but the area under the curve is the antiderivative, or the displacement. So if we measured the area under the curve, this area right here, while it's traveling up, would give you, if you calculated this, that would give you this height, right? This would be my height, if you like. So that would tell you how far it went from 0 to the height. But if you go all the way back to where it falls back down, notice the area under the curve, this would be positive, this would be negative, and so it would cancel out and would say it went a distance, a displacement, not a distance, but a displacement of 0 because it came back to where it started. Okay, so that's how you can get at this graphic. Some other things to note here that I want to point out is even though we have v equals 0, notice at this point, the slope is still minus 9.8. So it's possible to have a v equals 0 and our acceleration to be non-zero, to be minus 9.8 meters per second squared. And hopefully that makes some sense. Initially, some people are like, well, if the velocity is 0, how can the acceleration be anything? But if you have a 0 velocity, and you always have a 0 acceleration, that means it's never moving because an acceleration is a change in velocity. So whenever you start, then you must go from 0 velocity to some velocity, and there must be an acceleration that does that. Similarly, when you go up here, what's happening is your velocity is going from positive, so we go from v is greater than 0 on this side to v equals 0, to v is less than 0. So we have a changing velocity. So the velocity is going up and then going back down. But at that top part, if suddenly our acceleration turned off, then it would mean the ball is hanging there. Okay, so our acceleration is our change in velocity. So it's possible to have a 0 velocity and a non-zero acceleration. Similarly, you can have a 0 acceleration and a non-zero velocity. That's just going at a constant speed.